what resonance is. So sometimes there's more than one Lewis structure for a molecule. There's more than one Lewis structure for a molecule, and they only differ in the position of the electrons. Meaning I could have put the electrons pretty much, I could make that double bond in any of my choices, and all my choices were the same. Like say they were equivalent. So if I have more than one Lewis structure, these Lewis structures are going to now be called resonance structures. Okay? Resonance structures, meaning I had equivalence choices, and if I draw all of them, they all give me the same structure with only a difference in where that double bond or those electrons were. The actual molecule ends up being a combination of these resonance forms, and this is called a resonance hybrid. Doesn't mean that it resonates between the forms that we draw. It just means that I'm going to have a combination. Some are going to be the other, some are going to be one, some will be the other one, and it's kind of like an average. It's almost how you could think about it. How do we know if we have Lewis structures? You really want to look for multiple bonds or lone pairs on the central atom. So if I have multiple bonds on the central atom, or if I have lone pairs on the central atom, that's how I know if I have Lewis resonance structures. This isn't an extra step at the end. This would be, I could ask you, how many resonance structures does something have? Okay? So think about resonance as almost like an average or a hybrid. If I took these two dogs, okay, and had a hybrid, mated them and had another dog, then that hybrid would be an intermediate between the two. Here, I could have the double bond on this side or this side. It doesn't matter, it's the same. So these two are called resonance structures because they're the same. I could have put the double bond on this side or that side. It's just flipped over. So what actually happens is a hybrid of those two, the double bond here or here kind of thing. So how do I know the rules for resonance structures? How do I know if it's a resonance structure or not? So to be a resonance structure, you have to have the same connectivity. You can't move atoms and elements around. The only thing that's moving is electrons. So it has to have the same connectivity. Who's bonded to who? The only thing that's moving is those electron positions. Where is those double bonds located? Where are those electrons located? That's the only thing that can move. Resonance structures must have the same number of total electrons because they have to pretty much be the exact same molecule, just kind of like a flip version of them. The second row elements can have a maximum of 8 electrons, so remember if it's row 2, those can only have 8, bonding and non-bonding. Remember our octet rule. But remember the third row can have these expanded octets. So when we see expanded octets, that's usually right here. This is usually when we start to see resonance structures, when we get those expanded octets. So if I have a choice and I'm trying to figure out my resonance structures, you might have more than one resonance structure that are equal, but not all of them are equivalent. Some of them are better resonance structures than others. So how do I know what the best one is? The best one is that I want my overall formal charges. The overall formal charges must total the same. To be a resonance structure, they have to have the same overall formal charge. So if I add up all the formal charges, they have to equal the same. The better structures, if I'm trying to figure out what the best structure is, these guys have fewer formal charges. Remember I said that what I want is I want them to have 0. The best thing would be zeros. If I have to have a formal charge, I want them to be small. So better structures have smaller formal charges. Smaller meaning -1 versus like -2. -1 would be better than a -2. Better structures have a formal charge on the more electronegative atom. So if I have to have a negative, I want it on the more electronegative atom because that atom would rather have it. All right, so on the next slide, we're gonna just practice. So we haven't done one molecule from getting all the way to the end. So we're gonna practice from the very beginning all the way to the end, and we're gonna practice pretty much everything you could do in one molecule, okay? Because so far I've kind of broken down the steps for you into little bite-sized chunks. Now we're gonna do some examples where we do all of it together.